Presentation in Unit 6. It's called Physics is All About the Moments. It says one way to keep momentum going is to have constantly greater goals, and that's a physicist Michael Korda. So the learning goals for this particular presentation are that you be able to differentiate between inertia and momentum. A lot of times these terms are used interchangeably, but they have very different meanings. That you be able to relate momentum to force and motion, and that you be able to use the equation P equals mv, which is our equation that we have for momentum. So, here's what we already know. We already know that objects in motion have mass, and that's measured in kilograms, and we talked about mass first in the force unit, and you've talked about mass for a long time before that as well. We also know that objects in motion have a velocity, and a velocity is something that includes both magnitude and direction. And from the previous unit, we also know that things that are moving also have kinetic energy, which we call the energy of movement. What we learned in the lab is that when you increase the mass, you increase the momentum. And the momentum we defined as what the impact was on this particular styrofoam block. So as we added mass to the car, you found that there was a greater impact on the styrofoam block. You also found that whenever you increase the angle of the ramp, you also increase the velocity. And when you increase the velocity, you also increase the impact on the block or the momentum. We also know that whenever you increase the distance it's allowed to roll, the velocity also increases, and therefore momentum increases as well. So what we know is we know that increasing mass, increases momentum. We also know that increasing velocity increases momentum. So momentum we define as sometimes it's referred to as the mass in motion, and that's a pretty good description for it. Momentum requires two things. It requires both mass and velocity. So it's very similar to kinetic energy. Remember, kinetic energy was zero if the object was motionless. It's the same thing for momentum. The momentum is zero if the object is motionless. So unless the object is moving, it cannot have kinetic energy and it cannot have momentum. So it requires both mass and motion because it's a product of the two. Now we also know that momentum is a vector. Now a vector means it requires both magnitude and direction. So whenever you say it has 10 kilogram meter per second of momentum, you should really specify a direction such as right, up, down, left, something along those lines to make sure that somebody understands that it is a vector. So inertia. Now inertia is a little bit differently. Inertia is the tendency of an object to resist change in motion. We did discuss inertia a little bit earlier with force whenever we talked about the law of inertia. We're going to define inertia as mass. Okay, mass is the measurement of inertia or the tendency of an object to resist its change in motion. So here, momentum, you cannot have momentum if the object is motionless. Here, inertia we're going to define as mass. An object can have inertia if it's not moving. So we have the momentum equation. The momentum equation that we have is P equals mv, where this is actually a Greek letter rho, but we're going to go ahead and just call it lowercase p to clear up any confusion. So this is momentum. Momentum is a new variable in this particular unit. It is a combination or a product of mass times velocity. Now mass and velocity we're very familiar with, how to measure them and all those sorts of things from previous units. But momentum, on the other hand, is something new. It cannot be directly measured. It's a combination of these two terms. So it's going to be calculated all the time. And the unit that we have for momentum is going to be the kilogram meter per second, which is what we get when we multiply kilograms times meters per second. An example of this says, determine the momentum of a 5 kilogram bowling ball thrown at 14 meters per second. So if you look, it says determine the momentum. I know I'm looking for momentum of a 5 kilogram bowling ball. Mass is equal to 5 kilograms. Thrown at 14 meters per second. Velocity is 14 meters per second. So I have my given, I have my unknown. The next step that I have is I write my equation. The equation that I have is momentum is equal to mass times velocity. Take these values, multiply them together, you get 5 times 14. Multiply those out, you get 70 kilogram meters per second. In the next example, we have a proficient level example. It says a car is released from a styrofoam block and allowed to roll down a ramp into a styrofoam block as shown. Sketch the relationship between the distance the car is allowed to travel down the ramp and the momentum of the car as it reaches the bottom. So this is kind of a tough one right here because we've got to look at our axes here. We're trying to sketch the relationship between distance, which is what we're going to allow to vary, and then we're going to have momentum as something that depends on that particular distance. Now you know that momentum doesn't directly depend on distance, but for this experimental situation, the longer this thing is allowed to roll, the faster the velocity is going to be. So what I'm going to do is I'm going to look at my kinematics motion equations. Remember those? We have the initial velocity of the car, we have the final velocity of the car. That's what I really want to know because that's what's going to affect momentum. You know that's going to depend on the distance because that's what I'm looking at. And I'm also going to make sure it depends on the acceleration because the acceleration is going to be constant because the ramp is constant. So because of that, I can say that or final velocity is equal to initial velocity plus 2AD. Well, in each one of these cases, you can cross out a variable that's going to be considered a constant. Since we're only graphing distance and momentum, initial velocity is going to be a constant. I'm not saying it's zero, it could be zero, but it's going to be a constant. 2a is going to be a constant. So really what I'm down to is the final velocity squared, and it's not equal anymore. You can't say it's equal because we've crossed out these numbers right here. We can say is proportional to the distance. Well, if I'm looking at it, trying to turn this into a graph, I know that the final velocity and the momentum are proportional to each other. So what I can say is I can substitute this in here and I can say, okay, well, I'd like to put momentum in there, but momentum is proportional to velocity. So I can't do this squared thing. So what I'm going to do is I'm going to take the square root of both sides. When I take the square root of both sides, I get final velocity is proportional to the square root of the distance. Now remember, momentum is directly proportional to velocity. Now we're going to assume the mass of the car is constant. And when you do that, you get momentum is proportional to the square root of the distance. So what you would get is you would get a graph that looks something like this. It increases, but it's a square root relationship. So whenever you get to the distance being 4, then the momentum should be roughly 2. So you get this relationship, and you can see it on your calculator, or you can graph it. The last question is a mastery level question. It requires us to remember our knowledge of free body diagrams. Now remember, we spent a lot of time on free body diagrams in Unit 3. So it says determine the final momentum of a bike rider who's initially traveling at 4 meters per second and subjected to the free body diagram below for 10 seconds. So now remember, I'm looking for the final momentum. In this case, the final momentum, remember momentum depends on mass and velocity. So if I'm looking at the final momentum, that's going to depend on the final velocity. Now we're going to assume that the mass of the bike rider doesn't change throughout the experiment because it's not likely to occur. So what I need to know in order to solve this question is I need to know the mass. Now I do know the mass already. It's listed for me. It says, well, it's not actually listed. I have to get it from the free body diagram. Now since you have the free body diagram, you can say that the weight is equal to the mass times the gravity. Well, in our case, we know the weight is 490, we know mass is what we're trying to solve for, and we know gravity is 9.8. When we divide both sides by 9.8, we find out that the mass ends up being 50 kilograms. So that becomes one of the given pieces of information in calculating momentum. The other thing that I need to find is I need to find the velocity. So if I can find the final velocity, that's what I need once again to solve for momentum. But final velocity isn't given to me. Initial velocity is given to me, and that's 4 meters per second squared, or excuse me, 4 meters per second. I do know that the time that this thing is accelerated is 10 seconds. Now I need to use this free body diagram to figure out what the acceleration is. Now I can only do that by using Newton's second law. If you look, I have to find the sum of the forces. The force down and the force up cancel each other out because 490 up, 490 down cancel. I've got 50 newtons to the right, 40 newtons to the left, which has a net force, or a sum of the forces, of 10 newtons. Remember, I still have a mass of 50. What that will allow me to do is now solve for the acceleration. I can say the sum of the forces is equal to the mass times the acceleration, or 10 is equal to 50a. Divide both sides by 50, and you get an acceleration of 0.2 meters per second squared. Okay, so once you have that, you can now plug it in to IFDAT. I have the initial velocity, I have the acceleration, I have the time. I'm trying to solve for the final velocity. The only thing that I don't have and don't care about in this case is the displacement. So that's going to be the determining factor in picking the kinematics motion equation. So the one that I have that doesn't have displacement in it is acceleration is equal to the final velocity minus the initial velocity divided by the time. Well, the acceleration that I have is 0.2 equals the final velocity, which is what I'm trying to solve for, minus 4, which was my initial velocity, divided by the time, which was 10. When you multiply both sides by 10, you end up with 2 equals Vf minus 4. Well, that lets me know that the final velocity ends up being 6 meters per second. So now that I know that the final velocity is 6 meters per second, I can go ahead and solve for the momentum, and I'm going to go ahead and scroll down here. Remember, the equation that we have is momentum is equal to mass times velocity. I have a mass of 50. I have a final velocity of 6. When you multiply those out, you get 300 kilogram meters per second. Now, if you look at this example and say there's a lot going on there, you're right. You had to be able to correctly interpret a free body diagram. You had to apply Newton's second law. You had to apply IFDAT. Then you had to solve for the momentum. Now we're going to learn in the next unit that there's actually a shortcut for these types of questions. You can directly relate momentum to force in a little bit easier way called the impulse momentum theory. More on that in the next presentation.